So what we have here first is called the ratio test. So the ratio test. This one, yeah, like I said, I find it relatively enjoyable. So what this says is that we're assuming that this exists. So this looks like a fancy P. And when I first saw it, I thought the same thing. It's a fancy P. But it's actually called Rho. It's a Greek letter. One of the many Greek letters that you'll encounter if you move up and take more advanced math courses. So Rho is equal to limit as n goes to infinity of the absolute value of the a sub n plus 1 term over a sub n. So we're going to assume that this exists. And then there are three cases that could come out of it. So the first one is when rho is less than 1. Okay, so when this happens, then that means that the infinite sum of a sub n converges. I'll just write it out. Converges absolutely. Absolutely. And you can kind of tell, maybe not entirely or directly, but we can tell that it converges absolutely because we have this absolute value sign built in to the calculation of the rho or the fancy P. So that's the first case. The second case is for rho to be greater than 1. And in that case, then it's pretty simple. Our conclusion is just that the sequence diverges, or this series diverges, the sum. And the last one, as you might deduce, is when rho equals 1 exactly. Then that means that the test is inconclusive. Whoa, there's a big space in between. Okay, inconclusive. Okay, so this just means that the test told you nothing, nothing more. So it could still converge or diverge. Converge or diverge. We can't tell, basically. Okay, so let's do an example applying this ratio test. Let's say we're given the following infinite sums as n goes from 1 to infinity of n squared over 3 to the n. Okay, so in this case, whatever they give you here is basically just going to be your an, okay? And then, so our an plus 1, though, in this case, to get that, then you just plug in n plus 1 wherever you see an n. So a sub n plus 1 would be n plus 1. And I would suggest whenever you plug in n plus 1, put parentheses around it, just in case, to be safe. You can never have too many parentheses, in my opinion. So then we have a 3 to the n plus 1 up here. Okay, so now with these, we have to set up our limit, right, to find rho. So now we'll have that rho equals the limit as n goes to infinity of, and I'll just write this out. I'll write out the formula for familiarity sake so you guys can see it some more. And now we'll replace our a sub n plus 1 on top. So we'll have, and don't forget the absolute value, that's really important. So we'll have n plus 1 squared up here over 3 to the n plus 1. And then this is over a sub n, which is just n squared over 3 to the n. Okay? So essentially what we're going to do now is just simple algebra and simplify here. So I'll keep rewriting it over here. We have limit as n goes to infinity of, I'm just going to keep the top fraction the same. Actually, I'm just going to multiply out while we have the chance, so let's FOIL. Let's go back to some algebra. So we have n squared plus 2n plus 1 over, and down here we can actually break this up into 3 to the n times 3, right? Laws of exponents. And then we also have this one, this term here, this fraction is going to flip to come to the top. So we have 3 to the n over n squared. Okay, and as you can see here, the 3 to the n cancel, so that's good. And that's pretty much it. That's all that cancels as of now. So now we're just going to simplify some more. So we have a 1/3 here. We could technically take that out, or I'm just going to leave it in for now. That's just a trivial decision there. So we have a 1/3, and this is still an absolute value. And the rest of it looks like this. We have n squared plus 2n plus 1 over n squared. Okay? So this is that's what we've come to so far. But now what I want to do to evaluate the rest of the limit is divide up the numerator and put each one over, divide up the terms in the numerator to put it over the denominator. So I guess, well, I could squish it in here a little bit. So we'll have limit as n goes to infinity of 1 over 3, and then we'll have n squared over n squared plus 2n over n squared plus 1 over n squared. Okay? And as you can see here, the n squareds here cancel and make a 1. One of the n's cancel with one of the n's on the bottom. So we have a 2 over n plus 1 over n squared. And I'll continue this on the next slide for more room. So now what we have is rho equals the following. Limit as n goes to infinity of 1 over 3, that is a 3, times 1 plus 2 over n plus 1 over n squared. Okay? And then at this point we can just plug in infinity for n, right? So what we're going to get is rho equals 1 over 3. Whoa, my 3's are acting funny. But anyways, 1 plus 2 over infinity plus 1 over infinity squared. And these terms both go to 0. So this is going to end up being 1/3. So rho equals 1/3. Rho equals 1/3, which is less than 1, right? So the ratio test tells us, hold on. Grammatically, that's supposed to be a lowercase b. By the ratio test, we can conclude that the given series, converges. Exclamation point. Okay. So it's just that simple with the ratio test. You just set it up, see what your value for rho is, and then compare it to 1. See if it's less than, greater than, or equal to, and then you can make your conclusion. And sometimes your conclusion will be that the test itself is inconclusive, in the case of rho equaling 1. Okay, now onto the second test in this section. So this one is called the root test. The root test. Okay, so anything that you might think from root in math is basically what this is saying. So we're going to be dealing with some kind of roots here, not necessarily square ones or cube ones, but any kind of root. So we're going to assume the following. Assume that L, big L again, so this denotes the limit as n goes to infinity of the following. So this is, I put a 2. Okay, so this is supposed to be an n, sorry. So the nth root of the absolute value of a sequence. So we're supposed to assume that this thing exists. So assume this exists. Okay, so that's our only assumption. And then we're going to have, like the ratio test, we're going to have 3 different situations here. So the first one is when L, this limit, is less than 1. Then that means that the sequence converges absolutely. And just as in the ratio test, we can tell that it's absolutely because we have this absolute value sign built into the formula. The second option is when L is greater than 1. So just like in the ratio test, AN is going to diverge. Okay? And the third one, L equals 1. And again, just like in the ratio test, if we get this result, that the limit equals 1, the test is inconclusive. So it basically just didn't give us any more information as to whether the sequence converges or diverges or anything. Okay, so let's do a quick example of this, and we'll wrap it up for this video. So let's say we're given the series from 1 to infinity of the following. So now we'll have n over 4 n plus 7 to the nth power. Okay, so if we have this, we're going to assume, first of all, that this big L, the limit here, as n goes to infinity, exists. So we're going to have the nth root. Okay, so this is how you set up the root test. So we're going to have something in here, and this is going to be the absolute value of our a to the n. So this is a sub n, right? So we're just going to plug that in here, into this blank space. Allusion to Taylor Swift, sorry. That was unintentional. So, yeah, so we're just going to plug that in here, in between the absolute value signs. And as you can see, the power to the nth power and the nth root cancel pretty conveniently. And they try to do that on the homework, I believe, so just be looking out for that. So these are going to cancel, and we're actually just going to get the following. Big L equals the limit as n goes to infinity of just the inside. So n over 4, n plus 7, okay? And now we're just going to evaluate this like any other limit. So on the top, I'm just going to multiply times 1 over n on both top and bottom to simplify the top to 1. And then we'll rewrite this here. So then on top we have 1. And on the bottom, if we distribute this in to each term, we're going to get 4n over n, which is just 4, plus 7 over n. And now I can just plug in infinity. So our big L turns out to be 1 over 4 plus 7 over infinity. And this term right here cancels to 0, basically. And then, so our L equals 1 over 4, which, so L equals 1 over 4, which is less than 1. So this is our first case. So that would be that the sequence, so series converges, and this is actually absolutely, because we use the absolute value, by the root test. Okay, so that does it for section 11.5. And good luck on the homework. I'll be talking to you in the homework video if you tune in to watch.